Okay, let's talk about charged particles in a magnetic field. Charged particles, say we have, just for example, we have an electron. An electron is moving. If an electron or if charge is moving, then it will create a magnetic field. And if that magnetic field is inside another magnetic field, then what we have there is we have force interacting between these magnetic fields, because remember we said if their poles are alike they'll repel, if they're opposite they'll attract. So one way of drawing magnetic fields is we draw arrows, B, and go from north to south. So these are headed off towards the south. Now that's good. If they're going up we can draw them like this, but when we're dealing with magnetic field problems, often we're dealing with three-dimensional problems, so we need to have a way of representing all three dimensions. We can draw them going that way, but what happens if something's going that way or that way? So if it's going into the page, we draw the magnetic field as a series of crosses, or any field into the page. You can draw them like that as well. If it's coming out of the page, you draw them as a series of dots, usually with little circles, just so people can see what's of the page, so you can see what's happening. So I always like to think of them as like a bow and arrow, or an arrow. So an arrow will have fins or feathers on one end, and it'll have a pointy bit in the other, which usually you stick into whatever you're shooting. So if you can see the feathers, the flights of the arrow, then it's going away from you. If you see the pointy bit, the point, then it's coming towards you. And I've had first-hand experience when a rocket's come straight at my face and you can see the pointy bit. So we often will draw a magnetic field into the page so you can see the crosses, so the magnetic field's going that way, out of the page, coming up that way. Now, if we have a magnetic field, let's put a magnetic field in here, and then we have a particle, say take an electron, like a negative charge, and it's going through the magnetic field, then this will generate a magnetic field of its own. And that is going to create a force on the basically on the particle. Now the question is, how big is that and what direction is it going to be? Now the size is easy enough. Size is going to be F, the force, equals Q, the charge. Remember the charge is going to be in coulombs, times the velocity of the, that's going to be in meters per second, times the size of the magnetic field, and that's going to be measured in Tesla. Remember, Tesla is newtons per amp meter. Oh, we've got amp. And then whatever angle, sine theta, that the charge is happening at. So basically it says for the strongest, greatest effect, the electron has to be going right angles to the field. If it were going into the field, same direction as the field, sine would equal 0, which would equal, if it's going right angles, that becomes sine 90 equals 1. So that becomes the greatest effect. And what we can actually do is we can, to determine the direction of the force, to find direction, use the right-hand slap rule. Right-hand slap rule. There's a lot of right-hand rules in here. So basically, if this is my right hand, there's my fingers, there's my thumb, I stick the fingers in the direction of the magnetic field. I stick the thumb in the direction of the current. And that means that the force is going to be in the direction of the whichever way my palm's facing. So force, of course, is going to be measured in newtons. I should put that in here. So if we're going to look at this case, this is a little tricky. I will admit this. We stick the fingers in the direction of the magnetic field. The magnetic field's in the page. But the current is going the opposite way. Remember, we say current goes from plus to minus. So if the electron's going that way, current's actually going that way. So turn the hand around, so the force is going to be acting that way. So yeah, I mean that gets quite painful trying to figure it out. If it was a proton going in there, it would act the other way. So let's actually do a couple of exercises. Exercise 5.1. What is the force? What is F on a proton moving at 2 times 10 to the 6 meters per second, and they can go at an angle 45 degrees to a 0.5 Tesla field. So what we have to do there, so how are we going to do this? Well, we know, draw a picture. There's our field, boom, 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 and our proton, it's going to be a plus, it's going to be travelling at 45 degrees. So we can then use this equation here. Force is equal to QVB sine theta, and I'm going to have to go and check what the elementary charge is. It's like 1.609 times 10 to the negative 19, so high. Elementary charge 1.602 times 10 to the negative 19 coulombs. So what do we know? We know Q. So force, well, Q is equal to E, or elementary charge, which is equal, and it's going to be plus E, which is equal to 1.602 times 10 to the negative 19 coulombs. So we write that down there, 1.602 times 10 to the negative 19 coulombs. We know the velocity is over there, 2 times 10 to the positive 6 meters per second. We know the magnetic field is 0.5 Tesla. We know the angle is sine 45 degrees. So what we can do then, it's calculator time. So 1.602 x minus 19 times 2x6 times 0.5 times sine 45. Make sure your calculator is in degrees mode, equals 1.133 times 10 to the negative 13 newtons. And we have to ask ourselves, does this seem like a reasonable force? The answer is yes, mainly because a proton is a very, very, very small object. So that's actually part 2 of this question. What is the acceleration? Is the acceleration of the proton. And well, we know that, well, we can look it up. Mass is going to equal 1.67 times 10 to the negative 27 kg. Yep. So force is equal to mass times acceleration. Rearrange that. Acceleration is equal to force over mass, which is equal to 1.133 times 10 to the negative 13 newtons over 1.67 times 10 to the negative 27 kg. So let's go divided by 1.67 x minus 27 using calculator equals 6.783 times 10 to the 13 meters per second squared. So that is accelerating at 67.83 million meters per second. And yeah, they can do that. I mean, that's a scary thing. So what happens though is if we have, let's carry on, if we have a magnetic field, this is actually a trick that's used a lot in things like magnetic bottles and things. If we throw say a proton in there, throw it in there, let's figure out which way it's going. Right hand slap rule, we stick the fingers in the direction of the magnetic field, so into the page, thumb in the direction of the current because it's a positive charge, it's going in the same direction as my thumb. That means there's going to be a force acting at right angles. And in reality what this can do is this will actually loop around in a circle. And as I said, we use these things in things like particle accelerators, betatrons, cyclotrons, magnetic bottles. This is actually a well-known technology. If you're smashing particles in a large hadron collider, you can tell how big how heavy the particle is by how big the circle is. So what we can actually do is we can work out r, the radius, is equal to the mass times the velocity over q, so this is mass, velocity, over q, the charge, times v. And if you want some real fun, you can work that out for yourself. I'm not actually expecting anybody to try it, but so let's try this in exercise 5.2. Remember, if you want to, you can actually pause this. If you want a proton, so this is basically the same proton as we've had before, proton, but it's moving perpendicular this time, and a 0.5 Tesla field moves at 2 times 10 to the 6 meters per second perpendicular to the field. That's cool. What is the radius? What is the radius? And what we can actually say here is we draw a picture, we've got it there, it's going around in a circle. We know R is equal to mv q over b, which is equal to, well, what we worked out what the mass was before. The mass was 1.67. 7 times 10 to the negative 27 kg times the velocity, which is 2 times 10 to the 6 meters per second. We divide that by the charge, which we worked out earlier for a proton as an elementary charge, so it's going to be 1.62 times 10 to the negative 19 coulombs. And the magnetic field, which we said was 0.5 Tesla. Now again, it's a stick this all through the calculator, time 1.67 x minus 27 times 2x6 divided by 1.602 x negative 19 divided by 0.5 equals 0.0417 meters. So in other words, it's got when it goes around in a circle, the radius is about 42 millimeters, approximately 42 millimeters, which is cool. So we'll just carry this on in a second. We'll put a little bit extra in here which isn't actually covered in the notes, but we'll do that in a second.